uh, the derivation of the element stiffening of the element stiffness matrix, which is also cause some problem for some students. So I will explain this one again. Uh, First, no matter we use the differential equations. Okay, if we use the differential equations, and then we can solve the general solutions. And after we solve the general solution, also we can change the undetermined coefficients to the unknown nodal displacements. Okay, so then we can get the element stiffness matrix. And the derived element stiffness matrix, we can find the relations between the end displacements. We can say they are the ui, vi theta I, and vj theta j. Okay, the four elements in the displacement vectors, they include the vertical displacement, the rotations at the left end, also include the vertical displacement and the rotation at the right end. So that's the end displacement. Also, we have the member end force. Okay, so the element stiffness matrix can give you the relationship between the nodal displacement or the member end displacement and the member end force. Okay, so we can get four equations about these two sets. When we derive this element stiffness matrix, we didn't specify any boundary conditions. So the four end displacements, they could be any values. Also, it doesn't matter the physical meaning of the member end force. The member end force could be the part of the external loads, or the member end force could be the reactions. Okay, they can be either. So we didn't actually specify the physical meanings of the member end force. Okay, so the derived element stiffness matrix can be applied to some special case of the problems. For example, if we have the cantilever beam, for this element, we know the vertical displacement and the theta I, they are equal to zeros. Okay, but we could have non-zero vertical displacement and the rotations at the right end. And for this case, usually the external loads, they are applied to the right end, and the left end, they are the force come from the support, or usually we call them as reactions. Okay, even it is a cantilever beam, we include the vertical displacement and the rotation at the original equations. But if we know these two elements, they must be equal to zeros, we can just eliminate the first two columns, and we can get a set of new equations. But in these four new equations, we don't need the first two columns of the elements. since we know they will be multiplied by zeros. Okay, so you can just eliminate the first two columns. Okay, so we can change the original 4 by 4 matrix to a 4 by 2 matrix only. And the four displacement elements, we can eliminate the first two and keep the third and the fourth element in the displacement vector. And the 4 by 2 matrix multiplied by the 2 by 1 vectors, we can get 4 elements for the member end force. For the 4 member end force, the first two represent the reactions from the support. The third and the fourth element, they are the external loads applied to this element. Okay, so you will find the 4 by 2 matrix multiplied by the two non-zero nodal displacements can give you the end force. No matter the member end force, they are the external loads or they are the reactions. Okay, so it is only one case of the spatial structures, but we can still use the original 4 by 4 matrix to get this one. Okay, so there are many other spatial cases. We can use the general element stiffness matrix to get the solutions for some spatial case. Okay, if we know the element stiffness matrix can be applied to any end displacement, and also the member end force could represent both reactions or the external loads. So we can use those spatial cases to get part of the element stiffness matrix. Okay, so if we understand this concept, then you should understand that we can use some spatial case to get part of the element stiffness matrix, the small k matrix. And also it can help us to solve to get the entire element stiffness matrix. For example, we can use the spatial case 1. If we consider the cantilever beam, then for this case, we need only two end displacements. They are the Vj and the theta j. Okay, the Vi and the theta I, we don't need to consider them since we know they must be equal to zeros. Also, we have for these two, they are the external load. And for these two, they are the okay. So for this spatial case, there are two non-zero nodal displacements, and we can consider the four elements of the member end force. Two of them, they are the reactions. Two of them, they are the external loads. And so after you solve these two, you can get the first two columns no, the third and the fourth column. Okay. After you solve this spatial case, then you can get the third and the fourth columns of the small k matrix. And then you can solve the other spatial case. Then use this spatial case to get the okay. Then we can use the cantilever beam and the fixed end supports. It is set at the right end. Then after we solve these problems, we can get the first and the second columns of the K matrix. So if we combine the results of these two spatial cases, then you can get the complete the complete 4x4 element stiffness matrix. Okay. Also, you can use some other spatial case. For example, okay, if we have a case of this one, for this case, the theta I equal to the Vj equal to the theta j, they are equal to 0. And the Vi is not equal to 0. Okay, so if we got this case, then we can consider the force, the Pyi, which is the external loads, and the Mi, Pyj, and the Mj. They are the reactions. They are the reactions. So if we can solve the problems, usually you can set okay. So if we solve for this spatial case, it is a statically undeterminate structures. For these statically undeterminate structures, we got only one non-zero end displacement. Right now, the non-zero end displacement, which is the Vi not equal to 0. And then we can, if we can solve the problems with the specify the nodal displacement, the Vi equal to 1. And then we can solve the 4 end force. Right now, the 4 end force, one of these 4 is the external loads. Right now, the external loads will be the PYI, and the other 3 are the reactions. So right now, they are the PYJ and the MI and MJ. Okay, so if you can solve these 4 end force, then you can get the first column of K. Okay, so you can solve the first column of the K matrix. Okay. Also, you can solve the other 4 Ks. For example, okay, so for this case, the theta I is E non-zero, and the other 3, they are equal to 0. And for this case, you can get the second column. Okay. Okay, also you can use the other 2 special cases to get the third column and the fourth column of the K matrix. Okay. After you solve these 4 columns, then you can combine them together to give you the complete 4x4 element stiffness matrix. Okay, so there are, you can say there are infinite possibilities to get part of the element stiffness matrix. And you can say the final purpose of these derivations, we like to get the 4x4 element stiffness matrix. Okay. So far we can use many different special cases to get part of the element stiffness matrix. And the final purpose of these derivations, we like to get the complete 4x4 element stiffness matrix. So there is one suggestion. Okay, the suggested solution procedure, how can we get the 4x4 element stiffness matrix by the easiest way to get the results? First, set statically first, usually we will set a statically determinate structure. Okay. Usually we will set a statically determinate structures. And in your homework, you know, we need to solve the flexibility matrix. If the problems is a statically determinate problems, then it will be easier to solve the flexibility coefficients and also the flexibility matrix. It will be easier to get. So usually we just set a statically determinate structure. For plane problems, there are not too many statically determinate beam. Usually you got 2 choices. One is the cantilever beam. The other one is the simply supported beam. Okay. usually we just we got only two choice. One is the cantilever beam, the other one is the simply supported beam. You can choose either one. Okay, and uh, then solve the flexibility matrix. Okay, then you need to solve the flexibility matrix for these problems. The flexibility matrix multiplied by the end force can give you the end displacement. Okay, usually they are the external load. The F is the flexibility matrix. The U is the end displacement. Okay, so for the cantilever beam, usually we do not apply the external loads to the restrained degrees of freedom. For this case, the restrained degrees of freedom, they are the Vi and the theta I. The Vi and the theta I, they are restrained by rigid supports. If we apply external loads to these two degrees of freedom, the applied loadings will be resisted completely by the supports. So this kind of the applied loading will not give you any deformation in the element, or it will not give you any internal force in the cross sections. So usually we do not consider this type of the applied loadings. So for the cantilever beam, usually we just consider the Pyj and the Mj. They are the possible external loads. And for these two applied external loads, what kind of the end displacements you can get at the node I, since for this nodal point, it is restrained by the rigid supports. So the end displacements will always be equal to zeros. So for these problems, usually we will study the Vj and the theta j, Vj and the theta j. So for these problems, the end displacement will be the Vj and the theta j. The applied force will be the Pyj and the Mj. Okay, so the purpose of of these solution steps, you need to find out the 2x2 flexibility matrix. Okay, after you solve the flexibility matrix, then you can solve you can solve the inverse matrix of the F. So you can get the okay. If you use the previous studies, after you solve the flexibility matrix, then you can solve the inverse matrix of the F matrix. Then you can get the KBB matrix. The KBB matrix for these problems, it will be for this part of the matrix. And so this one is the PP. This one is which one is Okay, after we solve the KBB, then usually we can solve the right now the PB, they are the and the PA, they are the reactions. Okay, so so usually this case they are called for these equations they are called the equilibrium equations. Of end force. Okay, so we can solve the equilibrium equations between the consider the four member end force. Right now, we can solve the PB, and if we use the equilibrium equations, we can find the PA. Okay. Okay, so for this special case, the applied loadings can be replaced by the KBB times UB. You can get the KA. And if we multiply these two together, then we can get the KAB. Okay, so the PA is equal to the KAB multiplied by the UB. So if we combine the KBB and the KAB, then we can get the third and the fourth column. Then we can get the third and the fourth column of the element stiffness matrix. Okay. Okay. Then we can use the okay, since we know the K matrix is a symmetric matrix, so if we know the KAB, then we can put the KAB transpose to get the KBA. So the KBA will be the KAB transpose. Will be the KAB transpose. We can get the KBA. Then we know the KBA multiplied by the UA can give you the PB. Since the KBA multiplied by the UA, you can get the PB. You can get the PB. Then use the equilibrium equation again. Then you can use the L times PB and give you the PA. And right now the L times KBA UA. If we multiply the KBA by the UA, it can give you the PB. And in the previous state, we have already get the PA is equal to L times the PB. Then we can multiply the L by the KPA to get the KAA. Okay, so in this solutions procedure, we need only one special case. We need only one special case. Also, for this special case, since it is statically determined structures, so it will be very easy to solve the flexibility matrix, and then you can solve the inverse matrix, and then you can solve the equilibrium equations, and then you can get the complete element stiffness matrix. Okay, so let's take a break here.